I don't know how much you have achieved, but this is a question that could be asked, and you have the necessary tools to answer this question. And the answer to this, however, has a different meaning from now on, which is about sampling. Our new title, or the new chapter from the book, we can say. But we will consider this chapter very briefly. Okay, we will not go into the details. I'll just try to give you the key points regarding this. Again, it's a very digital signal processing topic. Therefore, for those who will take digital signal processing, they will greatly consider this topic separately by itself. But we have to know some necessary flavor ingredients of this sampling business. What is sampling? Sampling is the process of obtaining the discrete version of a continuous time signal. So it's continuous time to discrete time conversion. Time to discrete time conversion. This is what we mean by sampling, and the sampling process starts from here. At least in terms of theoretical background, this is the theoretical starting point of sampling. And what does this say? It says that if you have a signal, let's call this signal x of t as usual on the time axis. On the time axis, you need to start by multiplying this signal with an impulse train. And the impulse train is something like this. What happens when we multiply the two signals graphically? So this is P of t. The result will be such that the magnitudes of these impulses will be scaled according to the values at the positions of the impulses. So we will get another impulse train, sort of impulse train, but the values will have the values of x of t. In this question, I expressed the multiplication output as y of t, but since we will continue with this process, it's more reasonable to give a name to that related to xt. Let's call it xp of t, which is the multiplication of the two. And the result will be, with an envelope related to x of t as above, we have impulses. Like this, sort of. So these new impulses, as you see, will have now different scales. This is the initial step, initial mathematical step of sampling discrete time conversion, continuous time to discrete time conversion. However, as you see, this xp of t is still a continuous time signal. It's not a discrete time signal yet. The discrete time signal version, since these are separated by the sampling period, the time instances will be similar here. 0t, 2t, 3t, 4t, etc., 5t, whatever. So these are the impulses, but they are continuous time impulses. We put arrows at the top of these impulses. Be careful about that. This is not a discrete time signal yet. But these steps are, by the way, hypothetical, as I say. They are mathematical explanations of the mathematical meaning of the discrete time version with respect to the mathematical meaning of the input continuous time version. Of course, we don't have an impulse train generator inside the analog to digital converter, ADC. We don't do it like this, but this is mathematically the closest thing that we can express. the last step from here to the discrete time version is another hypothetical conversion of the horizontal axis to n instead of t, and expressing this thing as x of n, xd, let's call it. And this xd of n will have the same shape as xp of t. That is, the envelope is something like this, I don't know. But this time, the impulses will be discrete time impulses. They will not be continuous time arrows. Something like this. But another critical step is now the expression of the horizontal axis. The horizontal axis is n, the discrete axis. So this point is 0, and what is this point? What's the label of n here? Well, it is 1. And this is 2, and this is 3, 4, 5, 6. Because they are integerly indexed. We don't have capital T, 2 capital T or anything. They must be integers. So this is the mathematical flow from x of t to xd of t. But of course, the analog to digital converter is doing something else, perhaps inside the circuitry from here immediately to this point. So why are we doing this? Because we want to express the Fourier transform of this discrete time version with respect to, and express it in terms of the Fourier transform of x of t. They have a relation. Now, there are a few questions before expressing that to be asked. What are those questions? The most important question is, when we multiply x of t with, by p of t, we get this. Now, these impulses, or this discrete time version, they correspond to the same thing. It's just a discretization process from t to 1 and 2t to 2, etc. Are we losing something? In other words, from there, is it always possible to come up with the continuous time version, which is the inverse operation? This time it is a digital to analog conversion, in other words. Can we exactly obtain x of t? Is it possible? Perhaps no. Is it always possible? The answer is no, it's not always possible. But the better answer, or the good answer, is for some cases it is possible. And it's amazing, because we are losing a lot of information, the in-betweens, but by proper interpolations, for some signals, by proper interpolations, from there we can exactly obtain x of t. As a matter of fact, that is why we have digital music. Because digital music, as the name implies, has discrete time samples. It is computerized, analog to digital converted already. We have compact discs, CDs. We don't even have CDs nowadays. We have digital music directly downloaded from the internet, for example. So they are files and they are digital, but they do correspond to a waveform, sound waveform. Is that sound waveform the sound that we want, or is it a little bit different? We will see that they are actually the same. They are not a little bit different, except for the compression artifacts, because nowadays we have some compression standards as well. But that loss comes from reducing the file size. Without reducing the file size, that discrete version and this version could be identical. Okay, they would correspond to the identical signal. Why is that? That is from the mathematics that we will see. First, we have to answer this quiz question. What is the Fourier transform of this thing in terms of this one? That's fairly easy, but for that we need to first find the Fourier transform of the multiplication impulse train. P of t was the impulse train. What is P of j omega, the Fourier transform of that? We have answered this question before. Do you remember that? And it comes from the Fourier series coefficients of the impulse train. What were the Fourier series coefficients of the impulse train? 1 over t, always, right? So if they are 1 over t for all Fourier series coefficients, then the Fourier transform consists of 2 pi times that, which is 1 over t, and we need to insert impulses to the positions of the Fourier series coefficients, which are everywhere. They are also periodically extended. K from minus infinity to infinity, delta omega minus k times the fundamental period, the fundamental frequency, which is omega s, I will say. This is the fundamental frequency. What is the fundamental frequency of that periodic signal? It is 2 pi over the fundamental period. The fundamental period is capital T. The impulses are repeated at capital T, therefore that is the period. So you could rewrite this expression by saying omega s is equal to 2 pi over capital T, and put it here if you wish. Just write it that way if you wish, in other words. Now, why am I giving a deliberate name of omega s? Why am I using this term? Sampling, right? This s comes from the sampling, and omega s is the sampling frequency then, because capital T is the sampling period. So that's why we give a name of omega s. So this is P of j omega. Let's draw it on the axis of frequency. P of j omega, and that is impulse train. Therefore we have impulses like this. Of course, the separation of this impulse train is different from the separation of P of t. What's the separation between two impulses in P of t? It was capital T. Over here, what is that? Omega s. So this is, the first is 0, the second is omega s, which is 2 pi over capital T. This one is 2 omega s, this one is minus omega s. And as you see, they are inversely proportional. The separation between two impulses in P of t and the separation between these two impulses are inversely proportional to each other. If capital T is very small in that expression, very narrow sampling, then these omega s values will be very large because it is 2 pi over capital T. They will be very separated. If they are separated, the separation between the time domain impulses are a lot, then this time 2 pi over capital T will be small, and these will come closer to each other. So that is P of j omega, and we must somehow express x of j omega as well. Just like what we did in, what was that, modulation, the telecommunication modulation, the assumption of a triangular spectrum makes sense because it's easy to draw, but this is just an illustration. This is not, of course, valid for only triangular spectrum of x of j omega. It could be anything. But whatever it is, let's draw it like this. But we need to have some shape constraints on x of j omega. We must impose some constraints. That constraint is band limitedness. In other words, this x of j omega must start and end. And they are, of course, the bandwidths. Let's call these bandwidths by omega m and minus omega m. Let's denote it by this over the frequency axis. So this is x of j omega. It could be another shape, as I say. In the frequency domain, we need to convolve these two. Okay? Because in time domain we are multiplying p of t by x of t, so we need to convolve these two in the frequency domain. What is the convolution result? Some of the students are constantly asking me whether I will ask questions from the earlier topics in the final or in other things as well. As you see, we always come up with similar concepts. I will not, of course, ask you a convolution question, but in order to solve this question, you have to convolve these two. It's not a convolution question, but as you see. So let's convolve them. And convolution with impulses was very simple, if you remember. It is just these things, these triangular shapes or whatever shapes, to be replicated at the positions of these impulses. Every convolution with an impulse will replicate this triangle again and again. So there will be one term in the center at the position of 0. There will be another triangle at omega s, another triangle at 2 omega s, etc. And it will be periodical now in the frequency domain. This is 2 omega s, this is minus omega s. So what is this? This is x p of j omega. But I'm ignoring the scales for the time being. Let's also put legends of those scales. The value of these impulses are 2 pi over capital T, because every impulse is multiplied by 2 pi over capital T. And let's assume a peak value here, just for a label. Let's say it's A. So what will be this thing? It will be A times 2 pi over capital T. Sorry, A times 2 pi over capital T. So that will be the peak value. For the time being, I'm not very much interested in what this value is, A times 2 pi over capital T, because what I'm more interested in is to be able to go back to the original from this. And you should really take a look at this. Is it possible to retrieve the original triangle from these triangles? Or is the original triangle shape still inside this replicated triangles? And the answer is obviously yes. Here it is, for instance. As a matter of fact, it's also here and here. And from any of these, it is possible to retrieve this triangle. This means that after doing this kind of a sampling, it is possible to obtain the original continuous time shape. It is possible. We didn't lose anything. How can you do that, by the way? How can you extract this triangle from these replicated triangles? By low-pass filtering, of course. You apply a low-pass filter, an ideal low-pass filter, and that low-pass filter eliminates all the other triangles. It will only have this one, which is here. This means that the process of digital to analog conversion is nothing but low-pass filtering. So you have to apply a low-pass filter to this, and the low-pass filtered version of this will be this. It's impressive. This one is consisting of impulses, yet when you apply a low-pass filter, it will still produce the original x of t and nothing else. That's so simple. Digital to analog conversion is therefore simple. It is just low-pass filtering. What is analog to digital conversion? It is also simple. It is multiplication by an impulse train. And these two are the inverse operators, inversions of each other. They are the inverse systems, you can say. We have seen inverse systems, right? Is it invertible, I was saying. So this system seems to be invertible. Multiplication with an impulse train, that's a system. And the inverse of that system is low-pass filtering. Just low-pass filter and you get the original. But as you may already start observing, there may be cases where it's not possible to invert the system, and that is related with the choice of the sampling frequency omega s. What was this point? It was omega m, the bandwidth. So what is this point then that I'm showing you? If this is omega s, this point in the center is omega s, then this point must be omega s minus omega m, isn't it? This point here is omega s minus omega m. Now, there is a danger that we choose omega s a bit small, and then these two triangles will overlap, will come on top of each other. And that is the situation where we start losing information. Then it won't be possible to apply a low-pass filter and obtain the original triangle. The original triangle will be lost. It will be occluded by another portion of another triangle. What is the condition for that? Let's write it here. When they are merely touching each other, that is the position where omega s minus omega m. Normally this thing, omega s minus omega m, must be greater than omega m. Right? Because this point is omega s minus omega m, this point is omega m. This must be larger than this one. Which means omega s must be larger than 2 omega m. And this is the expression that you must nail and memorize all the time. There's a very famous name to that. And what is it saying? It is saying that the sampling frequency must be greater than twice the signal bandwidth, or the maximum frequency of the message. Let's write it. Sampling frequency must be more than twice the max frequency in message or in signal. And there is a name to that. It's famous with it's a famous scientist's name, and you already know it from circuit theory, I guess. Nyquist condition or Nyquist criteria. This is the Nyquist criterion for obtaining or for coming back through this process for the perfect reconstruction after sampling. If this Nyquist criterion is violated, if you violate it, then the situation will be something like this. This will be one triangle, and this will be another triangle at omega s, another triangle here. So as you see, the tail portions of the triangles are lost because this part is occluding the other part, and there will be a mixture of signals around here, the mixture of harmonics in the frequency domain. And from that mixture, you cannot resolve which mixture part corresponds to the signal, which components correspond to the other component. They are occluding each other. So it's a masking process, therefore. If you don't obey the Nyquist criterion, you have masking. The name of masking for this particular case is also used in computer games and in the cinema industry. In the films also they use similar terminology. That's the terminology of masking or hiding something in English. And that is called aliasing. An alias is a fake name, it's a mask that you may use in computer games. Are you using such things? For example, you give an alias to yourself and a fake name on the internet, for example, your Facebook accounts or your email address. I mean, there are some people whose email addresses are like pinklady@yahoo.com. Okay, so who is Pink Lady? We don't know. It's an aliasing. It is hiding. This is also having the same alias concept or the terminology. And if the Nyquist criterion is violated, it produces so-called aliasing. Okay, that's what it is. Okay. So the critical or the most important thing you have to take into account is that you must avoid aliasing. And by the way, don't read it as aliasing. It's a very common mistake made by the Turkish people mostly, for some reason. Even when you go to abroad, Turkish people still continue using the name as aliasing. It's not. Okay, it's aliasing, by the way. So this is the fundamental concept of sampling. It's the most important problem. You may be asked questions to avoid aliasing, not aliasing. Since I have said aliasing all the time, now I'll start using it that way. It's not. You must avoid aliasing. And for that, what can you do? Or what are you supposed to do? First thing is this x of t must be band limited. And if it is not band limited, then what will you do? Because we have taken the Fourier transforms of some signals, and for some signals, for those signals, we obtained an expression in terms of omega which extends to infinity sometimes. That's a problem. That means that you cannot sample them without aliasing. Or what you have to do is you have to apply an anti-aliasing filter. Apply anti-aliasing filter. But what is an anti-aliasing filter? It's a low-pass filter. You must restrict your bandwidth. For instance, let's erase from here. If your signal is having a relatively large bandwidth, like this. If this is your signal Fourier transform, then you must first apply a low pass filter to that and restrict it between minus omega m and omega m. But how are you going to choose this omega m? What is the anti-aliasing bandwidth? You must of course choose as large as possible, because otherwise if you selected too small bandwidth, then it would be too much low pass filtering. You are blurring your signal, in other words. You don't want to do that. We must have this omega m as large as possible, but it mustn't exceed some certain value to cause aliasing. You mustn't cause aliasing. And what is that? You must choose omega m to be less than half the sampling frequency, omega s over 2. So approach to omega s over 2 as much as possible. Let's give you an example. The analog to digital converters in audio systems are sampling at a sampling frequency of 2 pi times, since it's in the radians, that's why I'm saying 2 pi times 44.2 kilohertz. So 88.4 pi radians per second is applied. So So what is the what's a good anti-aliasing filter bandwidth that you can select? That must be less than 2 pi times 22.1 kilohertz. Usually it is selected as 2 pi times 20 kilohertz, for example. That's enough. In audio systems, this bandwidth is also sufficient for our hearing systems, because the maximum frequency that a normal human ear can hear is 20 kilohertz anyway. So first you have to apply a low pass filter at 20 kilohertz, chop the remainings. Those remainings you don't hear anyway. So get rid of them first before sampling at 44.2 kilohertz. Okay, this is audio analog to digital conversion then, for instance. But aliasing does not necessarily mean only the maximum frequencies, and usually in exam questions I ask something else. But we're running out of time. We will see more of these examples, and we will also see the low pass filtering and reconstruction process later. Let me give you briefly the idea why in some cases it is possible to have a sampling frequency which is not greater than twice omega m. It is less than twice omega m, but still there is no aliasing. How can it be? It's like a puzzle game. The situation is like this. If your signal is not low pass but band pass like this, then by replicating towards right and replicating towards left, it is not only required that your next reconstruction starts from here and here, for example, the right hand side replica. It may be even inside still. Do you see that? So you have this original, and the replica is, for example, here, like this, and they don't overlap. Still they don't overlap, because the original one was here and the replica is here, and they didn't cause aliasing. They didn't hide each other. Now of course the reconstruction process doesn't mean a low pass filtering, because if you apply a low pass filter you will have everything, some junk. You have to apply a band pass filter for the reconstruction from digital to analog conversion, but we don't care about how to do that. We only care about whether it is possible or not to isolate this band limited signal. And it is possible to isolate it, because if it goes to the right like this, then it also goes to the left like this. And as you see, they didn't hide each other. They are still isolated. So there are cases where Nyquist criterion is not necessarily correct for non-aliased sampling. Usually I ask questions like this. What is the minimum sampling frequency, I say, for example? And this is omega m. The correct answer, the proper answer would be the minimum sampling frequency is 2 times omega m. That is the original Nyquist criterion. But the minimum sampling frequency is not 2 times omega m. It seems to be much smaller than that, somewhere around here. You see that? Start thinking about that. We'll try to see other examples related to that. And another thing, we still didn't find the Fourier transform of this discrete version. We found the Fourier transform of this version. So how do we proceed from here to here? We will see next week. Okay? So let's give a stop at this point. Please drop your quizzes over there.